Imagine yourself on the brink of change, consumed by a desire to fundamentally transform your life. How do you achieve this? Where do you begin this challenging yet exciting journey? We'll explore how to transform not only your life but also your mindset and habitual actions. It all starts small, with changing daily habits. This is precisely the key to large-scale transformations. Just as a star, seemingly unchanging over a human lifetime, actually undergoes colossal transformations, so too can an individual's life be reshaped through consistent, incremental steps. This is part of a series dedicated to stellar evolution. Viewers will delve into the depths of celestial bodies to discover the processes that cause them to shrink into dwarfs or expand into planet-engulfing giants. We will uncover the secrets behind changes in stellar brightness and color, their transformation into planetary nebulae, and explosive novae. And of course, the fate of our Sun 5 billion years from now will be revealed. A star's evolution depends on numerous factors: its generation, chemical composition, the presence of relatives in a multiple star system, and the circumstances of the molecular cloud's collapse. However, the decisive parameter is the star's initial mass. This alone determines how long and in what manner the star will burn. It's no coincidence that when astronomers compare stars, stating one is larger than another, they most often refer to mass, not physical size. The Sun is a moderately sized star. There are celestial bodies much smaller than it, dwarfs, as well as giants that surpass it by hundreds or thousands of times. There are also tiny celestial bodies that began as future stars but failed to accumulate enough mass to initiate thermonuclear reactions. This occurs if the initial mass is less than approximately 13 Jupiter masses, in which case a giant planet is born, not a star. If the protostar's mass is between 13 and 80 Jupiter masses, a cosmic object with unique properties forms. At such a mass, gravity compresses the interior so intensely that the temperature rises to a level sufficient for deuterium, an isotope of hydrogen, to begin burning. Burning, in this context, refers to participation in thermonuclear fusion. If the object manages to accumulate 65 Jupiter masses, lithium also begins to participate in thermonuclear reactions. Deuterium and lithium participate in thermonuclear fusion at lower temperatures and pressures than other elements, which is why they are considered more easily ignited. Despite thermonuclear fusion occurring within these objects, they cannot be called stars. By definition, a star is a celestial body in which nuclear fusion involving protium, ordinary hydrogen consisting solely of a single proton, takes place. Due to the low intensity and instability of these reactions, as well as their dimness, these objects are known as brown dwarfs. They belong to spectral classes M, L, T, and Y and are located in the lower right corner of the Hertzsprung-Russell (HR) diagram, adjacent to red dwarfs. Although their existence was predicted as early as the 1960s, astronomers were only able to confirm the existence of brown dwarfs in the mid-1990s. This is because their low radiation output and insignificant size compared to full-fledged stars make observing such objects extremely challenging. However, thanks to advances in astronomical observation, particularly the construction of telescopes with mirror diameters of 6 to 11 meters, scientists now know of thousands of brown dwarfs. Interestingly, they were initially named black dwarfs. But this term did not stick because astronomers predicted the existence of another type of object for which that name was more fitting. These objects will be discussed later. Now that we've covered what isn't a star, we can move on to the smallest stars, red dwarfs. Their masses range from 7% to 60% of the Sun's mass. Unlike brown dwarfs, red dwarfs undergo hydrogen burning via the proton-proton chain mechanism. There is no universal consensus among astronomers regarding which spectral classes to include in the red dwarf category. It is usually limited to class M, sometimes including part of class K, and occasionally broader classifications are encountered. According to scientific estimates, red dwarfs hold the leading position in terms of numbers among our galaxy's stellar population. However, their prevalence isn't their only notable characteristic. These cosmic objects stand out for their astonishing longevity. Theoretical calculations indicate that red dwarfs can exist for up to 2.5 trillion years, which is 180 times the current age of the universe. Based on this, it can be asserted that in 13.8 billion years, not a single red dwarf has yet completed its life cycle. Furthermore, there's a hypothesis that some of them belong to the third, most ancient stellar generation, meaning they are among the very first stars to shine in the universe. Because all known red dwarfs are still on the main sequence of the Hertzsprung-Russell diagram, astronomers must resort to computer modeling to predict their evolution and later life stages. Due to energy transfer within these stars occurring solely through convection, the mixing of matter, helium does not accumulate in their cores, and therefore, its thermonuclear burning process cannot begin. Additionally, the convective mechanism allows red dwarfs to burn the maximum possible amount of hydrogen compared to more massive stars. However, sooner or later, hydrogen reserves are depleted, and the red dwarf gradually begins to approach the end of its existence. Unlike the Sun, which is destined to become a red giant in 5 billion years and potentially engulf Earth before shedding its outer layers, red dwarfs end their lives differently. This difference is due to their fully convective structure. Throughout its life cycle, a star gradually increases its luminosity. This is because as the concentration of helium in its interior increases, so do pressure and temperature. This, in turn, leads to the intensification of thermonuclear reactions and the faster burning of residual hydrogen. Consequently, the additional energy released in the interior must be dissipated in some way. This energy is emitted in the form of radiation, i.e. photons. However, inside a star, photons cannot travel in a straight line due to the extreme pressure and density of matter. They constantly collide with particles, are absorbed, and are almost instantaneously re-emitted. In fact, the matter inside a star is completely opaque to radiation. Near its center, the mean free path of a photon between collisions is only fractions of a millimeter. To illustrate, it's like trying to shine a flashlight through a steel railroad track. And this is despite the fact that the thickness of the matter layer a photon must penetrate is equal to the star's radius, in this case, tens of thousands of kilometers. Furthermore, red dwarfs have a significantly greater average density than the Sun. It is this colossal resistance that photons encounter on their journey into open space. However, if one imagines a flashlight with a power of approximately 10 to the power of 23 watts, such a light flux still penetrates, overcoming countless absorptions and re-emissions. As a result of this long and arduous journey, the star heats up, with the most intense heating observed near its center. Now, recall one of the key properties of convection: the greater the temperature difference, the more intense the process of matter mixing becomes. Thus, as the temperature in the star's interior increases, progressively hotter matter rises to its surface layers, and this process accelerates. Consequently, a red dwarf compensates for increased energy production in its interior not by expanding, but by raising its surface temperature. According to modern theories of stellar evolution, this process leads to a very interesting transformation. The red dwarf becomes a blue dwarf. It retains a mass of only a few % of the Sun's mass, but its surface temperature reaches 8 to 9,000 Kelvin. This corresponds to the temperatures of white-blue stars of spectral class A. Sooner or later, even a blue dwarf's hydrogen reserves are depleted. Thermonuclear reactions cease, and it begins to cool gradually. As a result of the temperature decrease, this object becomes red again, and then the peak of its radiation shifts beyond the visible range into the infrared spectrum. Thus, the red dwarf slowly transforms into a black dwarf, a star that changes its color for the last time and consists almost exclusively of helium. It's worth noting that the described theory remains hypothetical for now. No blue dwarfs have been detected yet, as none have had enough time to form due to the extremely long lifespan of red dwarfs. The universe is still too young to showcase these objects to us. Another interesting type of star is the so-called subdwarf. Originally, this name applied to luminosity class 6 stars, characterized by stellar magnitudes 1.5 to 2 magnitudes fainter than main sequence stars of similar temperature. On the Hertzsprung-Russell diagram, they are located directly below main sequence stars, forming a parallel line. Initially, such objects were called intermediate white dwarfs, but in 1939, Gerard Kuiper proposed the term subdwarfs. This category includes both white dwarfs and lower mass stars. In astronomical nomenclature, the term subdwarfs encompasses two entirely distinct classes of stars, hot and cool subdwarfs. Despite the apparent similarity in their names, their origins, internal structure, and energy generation mechanisms differ fundamentally. Similar to main sequence stars, cool subdwarfs derive energy from hydrogen thermonuclear fusion. However, their reduced luminosity is explained by their depleted metal content in their interiors. This specific chemical composition makes the star more transparent to radiation, allowing photons to escape more easily to the surface. This, in turn, leads to a decrease in radiation pressure, allowing gravitational compression to dominate. As a result, the star contracts, and the temperature in its core increases. Thus, contrary to their name, cool subdwarfs actually have a slightly higher core temperature than stars of similar mass but with a higher metal content. Hot subdwarfs, in contrast, are stars of spectral classes O and B. They are also known as extreme horizontal branch stars. These objects represent the late stages of massive star evolution, which will be discussed further in this narrative. Progress in observational astronomy in the early 20th century, combined with simplified access to research results, significantly accelerated the development of this science. It was during this period that main sequence stars were classified, distinguished as a separate group due to their characteristic location on the Hertzsprung-Russell (HR) diagram, which was also a product of that era. On this diagram, a clear straight line can be observed, extending from the lower right to the upper left. The primary characteristic of a main sequence star is the presence of hydrogen thermonuclear fusion reactions in its core, leading to the formation of helium. Main sequence stars include not only red dwarfs but also well-known celestial bodies such as the Sun, Alpha Centauri, Sirius, and many others. They can be divided into two groups: stars with masses less than 1.5 solar masses, and stars whose mass exceeds this limit. This division is due to the dominance of the proton-proton cycle in the interiors of less massive stars, while the CNO cycle prevails in more massive ones. Main sequence stars are in hydrostatic equilibrium, where the energy released from thermonuclear reactions is balanced by gravitational compression. Thanks to this, the size and temperature of main sequence stars remain relatively stable. Since hydrogen burning is the longest stage in a star's life, approximately 90% of all observed stars belong to the main sequence. At first glance, it might seem that larger stars, possessing a greater supply of hydrogen, should live longer. However, this is not the case. As a star's mass increases, the rate of hydrogen burning increases disproportionately. For example, doubling a star's mass also doubles its hydrogen supply, but the rate of its burning increases 10 to 15-fold. This is why the more massive a star, the faster it depletes its fuel reserves. The lifespan of stars can vary from millions of years, a very short period by cosmic standards, to trillions of years for stars with masses less than 0.1 solar masses. The upper mass limit for main sequence stars is in the range of 120 to 200 solar masses and is known as the Eddington limit. This theoretical limit means that stars with greater mass would possess too high a luminosity to maintain hydrostatic equilibrium. The radiation pressure in such stars would exceed gravitational compression, leading to mass loss through the shedding of outer layers. However, astronomical observations have revealed stars with masses significantly exceeding the Eddington limit, indicating the incompleteness of current knowledge about the laws of nature. After a prolonged and stable main sequence period, a star enters the subgiant phase. This term, introduced in 1930, describes a group of stars occupying an intermediate position between main sequence stars and giants. The mechanism of a star's transition from the main sequence to the subgiant stage depends on its mass. It's important to note that the terms subgiant and giant can be used not only to denote an evolutionary stage but also simply to classify large main sequence stars on the HR diagram. These primarily include bright O and B class stars. Not all of them are subgiants in the evolutionary sense, and conversely, not all evolutionary subgiants belong to spectral classes O and B. In this context, the term subgiant is specifically considered as denoting one of the stages of stellar evolution. Stars with masses up to 40% of the Sun's mass are fully convective. Throughout their lives, they burn almost their entire hydrogen supply, transforming into a helium sphere. Due to their small mass, helium burning never begins in such stars, and they gradually cool, completing their life cycle. However, stars with masses greater than 40% of the Sun's mass undergo much more complex and interesting transformations at the end of their lives. Unlike red dwarfs, Sun-like stars do not possess full convection. Energy is transferred from the core to the surface via radiation. Helium, formed in the core during thermonuclear fusion, is not carried away by convective currents. Over billions of years, as hydrogen burns, the star steadily accumulates helium in its core, where it remains. When the hydrogen supply in the core is depleted, only a helium plasma clump remains. Temperature and pressure are insufficient for further fusion, and reactions cease. The star loses energy, and gravity prevails. The star's contraction leads to an increase in temperature and pressure, and thermonuclear reactions resume, but now in a hydrogen shell around the helium core. From this point, the star enters the subgiant phase, although it's almost imperceptible externally. Hydrogen burning in the shell leads to the formation of increasing amounts of helium, which gradually settles into the core, increasing its mass and size. The hydrogen shell expands, generating an enormous amount of energy, even more than during core fusion. Excess energy leads to increased radiation, and the star inflates, growing 2 to 10 times in size. As it expands, the gas cools, and the star's temperature drops, shifting its color into the red part of the spectrum. Subgiants less massive than the Sun acquire an orange hue and a surface temperature of about 5,000 Kelvin. Despite the overall cooling, the star's luminosity increases significantly. This is explained by the increase in surface area, which is proportional to the square of the radius. A twofold increase in radius increases the area fourfold, and a tenfold increase results in a hundredfold increase. Although the temperature decreases, the increase in brightness remains substantial. Further evolution depends on the star's mass and metallicity. Stars with masses 20 to 60% of the Sun's can remain in the subgiant phase for up to 8 billion years, continuing to burn hydrogen in the shell and accumulate helium in the core. Eventually, the helium core becomes so massive that it contracts and becomes degenerate, meaning incompressible. This contraction is accompanied by a temperature increase, which accelerates thermonuclear fusion in the hydrogen shell. The star expands and reddens, transforming into a red giant. On the Hertzsprung-Russell diagram, the star moves to the red giant branch, where most such stars are found, for example, Aldebaran and Arcturus. These are enormous plasma spheres, very bright due to their large surface area, but with temperatures of 3 to 4,000 Kelvin. Stars less massive than the Sun shed their outer layers, forming planetary nebulae and a hot helium-white dwarf. Similar processes occur with stars 0.6 to 2 solar masses, including our Sun. They also accumulate helium in their cores until hydrogen is depleted, contract, and their temperature and luminosity rise despite the absence of fusion. In this state, a star can remain for several million years until the core becomes hot enough for hydrogen burning to resume around it. This reaction stabilizes temperature and luminosity, and the star begins to expand and cool. For stars of such mass, this evolutionary stage marks the end of the main sequence and the beginning of the giant phase. When the core accumulates sufficient mass, it contracts to degeneracy pressure and heats up. The star transforms into a red giant. When the Sun becomes a red giant, it will become too large for Mercury and Venus to exist. As it evolves, the Sun may expand 256 times, reaching a radius of 1.2 astronomical units, which exceeds the radius of Earth's current orbit. Modeling shows that our planet's orbit will change and become 1.5 times farther. However, other models, accounting for tidal effects, predict a smaller Earth orbit radius, so it's likely our planet will share the fate of Mercury and Venus. However, not all is predetermined for our star. Even at this stage of its evolution, the Sun is capable of a fight for survival. For stars whose mass is comparable to the Sun's, the contracting core can reach a colossal temperature of 100 million Kelvin. This is a critical threshold at which helium nuclei begin to fuse. In other words, helium burning is initiated at the very center of the star, forming carbon. This process begins rapidly, encompassing vast volumes of helium all at once, a phenomenon known as the helium flash. The conversion of helium occurs through the so-called triple alpha process, a sequence of reactions linking the proton-proton cycle and the C-nose cycle. Why triple, and why alpha? Alpha particles are commonly referred to as helium nuclei. The process begins with the fusion of two helium nuclei, resulting in the formation of an unstable beryllium-8 nucleus. Almost instantaneously, in a tiny fraction of a second, the beryllium nucleus fuses with one more helium nucleus, the third one, forming a carbon nucleus. This is the mechanism of the triple alpha process. It's important to note that at each step of this reaction, photons in the gamma-ray range are released, similar to the proton-proton cycle. Thus, an additional energy source emerges. This means the star simultaneously receives energy from two sources: hydrogen burning in the shell and helium burning in the core, a kind of double thermonuclear reactor. It might seem that with such an amount of energy, the star should expand significantly, but paradoxically, this does not happen. The energy released during the helium flash is expended on overcoming the degeneracy of matter in the core and initiating convection there. As a result, the star, on the contrary, loses some brightness, although it remains hundreds of times brighter than the Sun. At the same time, its temperature becomes higher than most red giants, reaching approximately 5,000 Kelvin. On the Hertzsprung-Russell diagram, this is displayed as the star's transition from a bloated red giant state to the so-called horizontal branch, where brightness decreases and temperature increases. This stage of evolution for the Sun and similar stars is significantly shorter than the main sequence phase, lasting about 100 million years. During this time, helium fusion continues in the core, with the gradual accumulation of carbon and oxygen. Eventually, helium reserves are depleted, and the core transforms into a carbon sphere. Thermonuclear fusion ceases, the equilibrium between gravity and radiation is disrupted, and the star begins to contract again, with its temperature rising. Since a significant amount of hydrogen and helium still remains outside the core, contraction leads to the ignition of helium in a shell surrounding the carbon core. In parallel, hydrogen fusion occurs in a second shell surrounding the helium-1. It is at this point, when the star has two active shells simultaneously, that a colossal amount of energy is released, leading to its renewed expansion and transformation into a supergiant. A striking example of such a star is Antares, whose luminosity is 13,000 times that of the Sun. This evolutionary phase is called the asymptotic giant branch, AGB, and represents a kind of swan song for a medium-mass star. Once both shells deplete their fuel reserves, the star's life cycle approaches its end. At this stage, the stellar wind blows significantly stronger than that of the modern Sun, leading to intense mass loss into space even before thermonuclear reactions in the interior cease. A significant amount of gas, ejected from its outer layers, forms around the supergiant. Ultimately, after all reactions cease, the outer envelope is completely shed, revealing a hot carbon-oxygen core, a white dwarf. It is still hot enough to emit high-energy ultraviolet photons, which ionize the surrounding expanding gas bubble. This spectacular, bright, glowing formation is called a planetary nebula. It's worth noting that this name has no connection to planets, or their evolution. William Herschel mistakenly believed these were the embryonic stages of star systems where planets form. In reality, he was observing their demise, but the name has stuck ever since. A striking example of stellar death is the V838 Monocerotis system. Between 2002 and 2006, astronomers, using images from the Hubble telescope, observed in real time as the star shed its outer layers. This was truly a cosmic spectacle. Finally, let's turn our attention to stars significantly more massive and larger than our Sun. The final stages of their lives are, without a doubt, no less brilliant and impressive. First and foremost, we must mention stars whose mass exceeds the Sun's by more than 8 times. These cosmic objects do not undergo a subgiant phase, as they are already giants themselves, classified as white and blue giants. After the depletion of hydrogen reserves in the core, thermonuclear reactions do not cease, and the core does not become degenerate. Instead, helium immediately begins to burn. During the fusion of helium in the core, which occurs in the star's final life stage, its color begins to change from blue or white blue to orange, and its surface temperature gradually decreases from tens of thousands of Kelvin to 4 to 5,000. The star's size significantly increases during this process, and it transitions into the supergiant category. Very massive and luminous O-class stars, whose mass exceeds 16 solar masses, swell to such sizes that they exceed the upper limit for giants and immediately become red supergiants. However, the proportion of such stars is small, as the more massive an object, the rarer it is in the universe. Truly fascinating metamorphoses occur in stars whose mass exceeds the Sun's by more than 8 times. When the helium reserves in their cores are depleted, their colossal mass allows them to continue synthesizing elements, progressing beyond carbon. Within these cosmic furnaces, reactions involving silicon, magnesium, and other elements unfold, up to the point of iron. Each new reaction ignites at the very center, while previous ones continue in the outer layers of the core, pushing lighter elements away from the central region. As a result, the star develops a layered structure, resembling an onion. Remarkably, most chemical elements up to iron, which constitute the universe, originated precisely through nucleosynthesis within the hearts of these stellar giants. The atomic nucleus of iron possesses the highest binding energy per nucleon, meaning any nuclear reactions involving it, whether fission or fusion, absorb energy. Consequently, iron cannot serve as fuel for further nuclear transformations and remains in the core of a massive star as an iron heart. Meanwhile, the temperature and pressure within the star's core continue to rise relentlessly, reaching a critical point where electrons are forcibly compressed into protons, forming neutrons. Of course, from a quantum mechanical perspective, this process is far more complex than attempting to squeeze a tennis ball into a basketball. In reality, protons and electrons possess a certain softness and readily merge into a single particle. However, the challenge lies in bringing them close enough for fusion. The proton and electron must overcome a critical barrier, aided by immense pressure and the extremely hot plasma where electrons are stripped from nuclei. Thus, the fusion of protons and electrons occurs almost instantaneously, encompassing a vast number of atoms. As a result, the once giant core of the massive star, which surpassed some small stars in size, transforms within seconds into a tiny neutron sphere merely a few tens of kilometers in diameter. Such extreme compression leads to the formation of a void at the very center of the star, which can no longer support the overlying layers, causing the entire star to rapidly collapse. Its outer envelope plunges onto what was once the core at a significant fraction of the speed of light. At this incredible velocity, matter crashes into the dense and massive neutron core. The colossal energy released by the infalling matter triggers an explosion of unprecedented power, a phenomenon known as a Type II supernova. For a brief period, energy equivalent to the output of hundreds of billions of ordinary stars is unleashed. Consequently, a supernova outburst can outshine the entire galaxy in which it resides. Other types of supernovae exist, which will be discussed at another time. Despite the colossal energy of the explosion, the star does not completely disintegrate. If its initial mass exceeded 8 solar masses, a mysterious object remains after the explosion, a collapsed neutron core, known as a neutron star. Along with black holes, neutron stars are among the smallest and densest objects in the universe. Typically, their radius is about 10 kilometers, and their mass exceeds 1.4 solar masses. This is known as the Chandrasekhar limit. The question of the upper mass limit for neutron stars remains a subject of debate, as various theoretical models yield fundamentally different results, ranging from 1.8 to nearly 3.5 solar masses. Inside a neutron star, thermonuclear reactions do not occur due to the absence of reactants, so it merely cools down gradually. However, it can evolve by interacting with other celestial bodies or by accreting matter from the atmosphere of a companion star in a binary system. Neutron stars get their name because, according to prevailing models, they consist almost exclusively of neutrons. These objects are prevented from further collapse by neutron degeneracy pressure, similar to how white dwarfs resist compression due to electron degeneracy. In addition to degeneracy pressure, more massive neutron stars utilize nuclear forces to counteract gravity. However, calculations show that for neutron stars with a mass exceeding the Tolman-Oppenheimer-Volkoff (TOV) limit, gravity triumphs. Depending on the chemical composition, this limit varies from 2.2 to nearly 3 solar masses. The most massive known neutron star has a mass of about 2.35 solar masses. If an object's mass exceeds this limit, it must collapse into a black hole. Thus, the Oppenheimer-Volkoff limit also represents the lower mass limit for black holes. Nevertheless, the least massive known black hole surpasses the Sun by 3.8 times its mass, so the precision of this limit's calculation remains an open question. Young neutron stars, freshly born, possess colossal surface temperatures, reaching tens of millions of Kelvin. However, lacking internal energy sources, they are destined for inexorable cooling. For example, a neutron star with a difficult-to-pronounce name has an average surface temperature of a modest 434,000 Kelvin. In comparison, the Sun, which gives us life, has an effective surface temperature of only 5,780 Kelvin. But of course, one cannot overlook the most astonishing feature of these celestial bodies: their incredible density. A mere teaspoon of neutron star matter would weigh several billion tons. Beyond their density, neutron stars are also renowned for their dizzying rotation speed. Surely, everyone has observed how a figure skater, by pulling their arms close to their body, dramatically increases their rotation speed. Something similar happens with neutron stars during their formation. As they contract, matter concentrates closer to the center of mass, and the rotation speed increases in accordance with the law of conservation of angular momentum. Young neutron stars can complete up to several hundred rotations per second. Among the known objects of this class, the record holder is a star rotating at a frequency of 716 revolutions per second, equivalent to 43,000 revolutions per minute. Some neutron stars emit narrow beams of electromagnetic waves, with the axis of these beams often misaligned with the axis of rotation. Such stars are known as pulsars. Under certain circumstances, these beams are periodically directed towards Earth, which we register as a periodic signal. Scientists estimate that there are about 1 billion neutron stars in our galaxy. However, many of them have existed for so long that they have cooled significantly. The electromagnetic radiation from such objects is extremely faint, so most known neutron stars have been discovered in specific situations, for instance, when they are pulsars or part of a binary system. Similar difficulties arise in detecting black holes, another outcome of stellar evolution. These enigmatic objects are detected solely by their gravitational influence on surrounding matter and electromagnetic radiation, such as visible light. Let's pause here, as many more fascinating details of stellar evolution await us, particularly concerning how stars interact in binary and multi-star systems.